right there.
DS?
Well, according to this, it would just be what? D theta times the letter R, right? Because that's what this, like here, if I was on a circle, and this was theta, and when you go, what's the length from here to here? It would equal R times theta. But here it's really cool, so I'm just going to draw an arrow here and just go, this little portion right there, that little arc would equal R times d theta. Similar to this. Cool. So, in the end, what is the area of that infinitesimal polar rectangle? Now I'm going to shade it in. That little guy. Do length times width. We call it a polar rectangle. What's length times width? Even though it has that little tiny arc to it. What would you get? dr d theta times a what? Times an r. So put this in your notes, everyone. This is going to be equivalent to the dx dy we had before. Or the dy dx. Every time you go polar coordinates, we're not going to write dx dy. This is that dA. I'll put that here. Just leave this up the whole class. This is your dA. Remember how dA would always equal dx dy or dy dx? When we go polar, what are we going to use? dr d theta, but don't forget what letter? R. So you'll be saying that over and over as a reminder. Don't forget to put that little letter R. Does everyone see how that emerged? Because that's what comes out of that in terms of an infinitesimal polar rectangle. We're saying that's dx dy in rectangular coordinates. But if we go polar, you got to put an r d theta in your image. Cool? If it helps everyone, it sounds silly, but sometimes it helps a student. Just think like a pirate, you know, like the pirate who goes RDR, you know what I mean? Like RDR. Just think of that when you go in polar coordinates. Think like a pirate. So you don't forget what letter.
Oh.
That R. RDR. It's RDR d theta is what we're going to use for the dx dy. Okay. So, can you help me do this? We're going to do a problem just like that. What was it projected over? The entire disk with the radius of 2. And there's the circle with the radius of 2. And you got to evaluate this integral projected over that region. Find the volume underneath this surface over that region. We don't want to go Cartesian, do we? We want to go what? Polar. Well, first of all, what am I going to put in place of that? What am I going to put in place of this? This becomes what?
R d
R d theta. Very good. Here, I'm going to guys, don't forget your R d theta. But I can't leave this, can I? And we're going to have to replace that x with something, and we're going to have to replace that y with something. Don't worry, don't think the problem's getting more complicated. This problem's going to get a lot easier. So when we have to put something else on the board. When we convert to polar coordinates, what does x represent and what does y represent? To do that, all we need is a nice right triangle. So I can put it here. You know what? I think I'll put on this board here first, and I'll transfer it to here. This is all we need to go into polar coordinates. So would you just build a triangle? All right, 90 degrees, that's the x-axis, that's the y-axis. Call this length x, call this length y, and call this radius r. And put a theta there. And do a little SOHCAHTOA, and you'll know the conversions. Okay?
R cos theta x.
So, cosine of theta is x over r. So, x is equal to?
R cos theta.
R cos theta. Radius times cosine theta. SOHCAHTOA. What's sine of theta?
Y.
Y over r. So what's y equal to?
R.
R sine theta. This is all we need. This is what we're going to put in place of the x and y. Now we need one more equation. Everyone, can you just do Pythagorean theorem for me? What's x squared plus y squared?
R squared.
Alright, cool. So if we get an x squared plus a y squared, we can just replace that with a r squared. I will leave this up all class. The reason I want you to do that with me, so if you're ever stumped on a test, it could be the final exam. You go, oh, I want to go polar on this. I'm dealing with the region of integration that's a circle. You can generate that right away with SOHCAHTOA trigonometry, convert to polar. Hey, if you want one more equation, can someone give me the equation for theta? Just if you're curious, I don't think you'll ever need it. It's just a gauge. You know what theta would equal?
Tan
Inverse
inverse
tangent of y over the x, right? If you want an equation for theta. Cool. Hey, all points in polar coordinates, that point right there will be plotted as radius comma theta. We always plot it as r comma theta. So polar coordinates, I'll put this here. Everything is plotted as r comma theta. And let me draw that triangle again. Theta, y, x, r. What's my main equations? X equals r cosine theta. Y equals r sine theta. And x squared plus y squared equals
R square.
r squared. There we go. And if you want to put that one as well, you can. We'll only put it down if we need it. Okay. So let me get this mess out of the way. There's your region of integration. And you're only going to project this over that disk right there. So we're going to have to set that up here, right? We'll come back to that. You draw that circle right there. So we're going polar on this. That would be crazy in rectangular coordinates. We didn't forget our RDR. What can I put in place of that x? R cosine theta. And what do I put in place of the y?
R sine theta.
R sine theta. So R cosine theta plus R sine theta. What else was sitting right here? The pirate RDR. So this is going to be your r's, your limits of integration for r. That's going to be easy. This is going to be a thetas. That's going to be easy. I say we start with theta. Anybody know what theta would have to be? Put it in radians to do a full circle. Remember, standard position, start here. 0 all the way to what? 2 pi. You got it? In fact, won't that always be the case if you got a full disk? Polar coordinates, piece of cake. What's your radii though? So for radius, everyone, you got to go from the pole, which is the origin. In this shaded region,
Negative.
I went from 0 to 2, 0 to 2, 0 to 2, 0 to 2, this whole region, right? 0 to 2, 0 to 2, because in terms of a radius, when we're doing polar coordinates, you go the distance from the origin out to the edge of the curve. So this will be from 0 to, and I'll write that really big up here, and look what we have now. This will be way easier to solve this problem. R cos theta, R sine theta. A lot easier than going Cartesian. DRE theta. I did this on purpose. What did I forget? R. RDR. You can put that R here too. So everyone, we'll solve this. And when we're done solving this, I'll put this on the board so you can say, what do we always do in polar coordinates? We always put the RDRE theta. And we get everything in terms of R cosine theta and R sine theta. Nice. Now let's work the problem. What do we get for this answer? What is the volume under that plane or that region? Can I break this up into 2 separate integrals? The rule of thumb, there's 2 things have to hold. These have to be 4 numbers, are they?
Yes.
Okay, they're 4 numbers. Can you rewrite this as just r's times just stuff in theta? I think you can. I'm hearing, yeah, I think we can. Does everyone see this? So I split it up if I can, just to avoid doing the iterated integral. Can I factor out an r? So if I factor out an r, what do you have? That's how I would approach this problem. You factor out an r, what do you have in the parentheses? Cosine theta plus a sine theta. Now I can multiply this r to this r, and what do you get?
R squared.
R squared. So then I am going to split this up. I just think it'll be easier. Here. I'm going to do 0 to 2 pi of cosine theta plus sine theta d theta. And I'm going to multiply that to the integral from 0 to 2 of the r squared dr. This is how easy this problem is going to be. Way easier than if we went Cartesian. That's my point. I know you know how to integrate that. This doesn't even need a u sub, right? Hey, I'll start here. What's this?
1/3 r cubed.
1/3 r cubed. Go from 0 to 2, you get 8/3. Okay, we're going to multiply that number to this. What's the integral of cos? Sine. What's the integral of sine? Alright. You got to go from 0 to 2 pi. Alright. So I get 0 minus 1 minus 0 minus 1. Now take this entire number right here and multiply it to that. What do you get? What's 0 minus 1 minus 0 minus 1? Uh-oh. And we're like, did we make an error? Well, we didn't make an error. Right? This is correct. We did the antiderivative correctly. We know what the sine of 2 pi is and the cosine of 2 pi, and the sine of 0 and the cosine of 0. 0 times 8/3. What's the answer to this integral?
0.
So what's that integrate? Now I kept saying the word volume. Well, it's really net volume. Because what could happen? Over that what? Over that region I had, the plane z equals x plus y might have done what? And half of the plane could be underneath the xy plane, and the other half could be above. And that's why it's coming out to be 0. I didn't want you to freak out when you get zeros or negative answers like, did I do something wrong? No, that's exactly what's happening. Cool?
Then how do we find the true volume?
Oh, for this?
Yeah.
They'll never actually like find that true volume for that unless they ask you to, they give you a surface that's totally going to be above the xy plane. So if they give you something that's always above the xy plane, then they can ask you to find that actual volume of that. So I'm trying to think of some example like something that you know that's always going to be above that. Like I'm thinking of something like that. Z equals x squared plus y squared. Isn't that a paraboid? I'm going to draw this just so you can see it here. And we go, alright, that's a paraboid. And let's say you had to find the volume of the solid formed by this paraboloid. I'm going to go up to like z equals 9. And underneath that plane, but bounded below by this paraboloid here. So it's bounded above by the plane z equals 9, but bounded below by this surface. We can actually visualize that. We can see it's what? It actually has a certain, actual volume to it. Nothing's below the xy plane, and we're able to solve that. So that's where they would ask that. Good question, though. So if they ask you to find the actual volume, they're giving you something that's going to actually be above that xy plane.
Hey, great job.
Hey, on that note, can we do this? This is not a bad problem at all. I like your question. Can you help me find the volume of that? I do want to point out, this is the volume of a solid bounded at the top by the plane z equals 9. Can you tell it forms a circular disk? Cool, it's the plane z equals 9 now. It's just because it's a circular paraboloid. And it's bounded below by this surface right here. Remember, that's the surface. So this is below. This right here, I'm going to put an arrow. That's z equal to x squared plus y squared. And the top portion is the what? Z equals 9. Cool. So I'm going to write this up. Got my number? Can you think about what's this getting projected over? This is the region of integration. So can you think what this projects onto the xy plane? Think of it as a projection, the shadow. What is the projection of this onto the xy plane? Can you all see it's a circle? It's the widest circle ever encountered by that solid. And they call that the projection. So I'll put that here. This is that projection. Can you all see what that circle's radius is? I don't know if you can. What's the projection onto the xy plane? It's a circle. Or I should say disk, because of everything inside of it. Let's call it a disk. What's its radius though?
3.
Amazing. You all knew. I didn't even do any algebra. You know that. How did you do that? How did you know it was a radius of 3? Because you set this number equal to that. Do you follow me? So I'm going to do that. They knew this because they actually told, when does x squared plus y squared meet the equation 9. When does x squared plus y squared, that's a z, equal z equals 9? So x squared plus y squared must be equal to 9, giving you a radius of what? 3. So this is the projection. So when we set up our right there. When we set up our region of integration, we're talking about this. So already I know we should do what? We're going to go polar eventually, right? Because of region of integration. But that's just going to set this up. What goes here? This is the what? The surface. But the surface, everyone, do you notice something? It's the surface, that region that we're talking about, it's bounded between the what? Between the 9 and the what? The x squared plus y squared. So I would have to write that here. Right? Oh, this, I would have put this right here if I was talking about this stuff here. But to talk about this here, Aiden, I gotta write, we're talking about the 9, subtract the x squared plus y squared. You follow me? That's how we gotta think. Does that make sense? And just to be, so you can, if you want to make a comparison and put it in your notes, you go, if you were getting the volume underneath this surface, over that region. Oh yeah, this would have just said x squared plus y squared. Because that's that actual surface. Now, you ready to go polar? Here, I'll just put a dA here. dA means, hey, you can stay Cartesian, or you can go polar. Let's go polar. What would this turn into? Go polar, alright. You all agree 0 to 2 pi? What's the radius? 0 to 3? Right? D or D theta, what letter I need? Automatic R, right? I already R in the Pirates, so I'll put it in front so it stands out. There it is. Now, what does this become? 9 minus, I need some help. What would you put in place?